index methods you're not using. My name is Jess Borland, also known as Girl Geek on Twitter. I am a consultant with Brent Ozar Unlimited. I do a lot of SQL Server performance tuning and help what's going on in our server right now. I have some letters after my name. I've helped co-author a book, but really what I like to do is talk about SQL Server and solve problems in it. One of the problems I'm going to help you solve today is figuring out what are some special index methods that I can use to solve specific problems in my database application. So first, let's start this by going on a SQL safari. Yes, let's talk about some common African animals. Let's start with the elephant in the room. The African elephant is one of the largest land mammals. It has large ears that are very sensitive, so it can hear predators sneaking up, and it's a very intelligent animal. I would equate this to the clustered index in SQL Server, which, when you create a clustered index on a table, contains all of the data in the table. If there are no other indexes that can satisfy a query, SQL Server is going to use the clustered index, kind of like the elephant will use its ears to listen for things. So the clustered index, failing any other indexes, will be there for you. Now, another very common animal, and what I personally consider the most adorable animal on earth, is the giraffe. So the giraffe is well suited to its individual environment. It has a long neck, so it can reach food that other animals can't. It has leopard-like spots which help it hide from predators. The non-clustered index in SQL Server is very similar to this. Non-clustered indexes are created on one or more columns in your table and help you get information for very specific queries without necessarily needing to scan an entire table. But beyond just a basic non-clustered index, we also have the Okapi. The Okapi is an animal that is very rare. It is only in the highlands of Rwanda, but it's particularly well suited to its environment. It also has large ears that help it detect predators that are coming. It has a long tongue that's very useful for eating vegetation that's out of the reach of other animals. It is actually, despite the stripes on its backside, more closely related to the giraffe than to the zebra. So within SQL Server, we have some index types that I would call the Okapis of SQL Server indexes. Today, we're going to talk about index options that are rarely seen but well adapted for certain situations. Indexed views, filtered indexes, and compressed indexes. For each topic, I'm going to talk a little bit about how we go about creating them, what the benefits are, what some use cases are for them, limitations if there are some, and trust me, with each of them there are some. And this is a really demo-heavy session, so I'm definitely going to be showing you examples of each of them. So let's start off with the first, which is indexed views. So a view in SQL Server is basically just metadata, right? When you create a view, it doesn't, when you create a view, it does not persist the data on disk. How can you make it do, so when you query a view that perhaps has many underlying tables or performs aggregations across a large data set, the SQL Server has to do a ton of work. There's nothing that persists this on disk unless you were to materialize the view. So you can create a unique clustered index on a view. The next query that runs that could use that index will create the index. So suddenly it is a persisted object on disk. Running this can be much more efficient than querying all of the underlying tables. So what are common uses for indexed views? The two big ones that I see, number one, tables that are joined together frequently, particularly when there are many tables and you're only accessing one or two columns from each of the tables. Having to read multiple tables can result in a lot of extra I/O. Another frequent use for it is reporting style queries that do a lot of aggregations. Doing things like summing, counting, etc. can be really resource intensive within SQL Server. Being able to kind of pre-aggregate this by having the information persisted on disk is going to make the queries faster. Now, with this note about what it's good for, I'm going to tell you when to avoid indexed views, especially if you're dealing with a lot of aggregations. You want to avoid using them if the underlying columns in the tables are frequently updated. Considering that every time you insert an update or delete a record on a table, any affected indexes also need to be updated. An index view is merely another type of index on a table. So, if you are frequently performing inserts, updates, or deletes against the underlying tables, you're going to have to do the same rights to the indexed view, and it can negatively impact performance. Now, let's talk about other requirements for setting up an indexed view. There's definitely a few rules that need to be followed. When you create the view, you have to include the with schema binding option. That makes sure that the underlying tables can't be changed if it would affect that view negatively. The tables must be in the same database. You can only create indexed views on tables. You can't create them on other views. You have to use a two-part schema.table naming convention. Your expressions within your view have to be deterministic. They have to return the same information. For example, you can't use getDate. That's not deterministic. That will change every time the query is run. But you could use a dateDiff function because when you pass in two values, that number will always be the same every time. So there is quite the list. As a matter of fact, if you go out to the Books Online article for indexed views, you'll see this lovely graph that I'm showing next in my slide deck. You'll see that there are certain things that the query, that the select statement can't contain. For example, count. You can't have subqueries. You can't have top. You can't have min or max. This can definitely narrow down the queries that you can use an indexed view for. However, you could still, if you have some base underlying tables, create an indexed view and then perform some of these aggregations on the view itself rather than trying to make a big, complicated, messy query. And that's another one of the things that I see indexed views being used for a lot. Sometimes we try to solve business problems or calculation problems with just one query. And that means the query can get bigger and uglier and longer and take more time. Sometimes it helps to just step back a second and say, okay, can we break this down into steps? Could we create an index view and then run some queries against that to get the same information? So let's go ahead and look at a demonstration of the indexed view. I am going to be running this against my SQL Server 2012 instance. However, all of this index view will work on SQL Server 2005 and greater. So let's go ahead and set the stage. I am using the AdventureWorks 2012 sample database. I am going to clear my plan cache so that we can get fresh query statistics and plans. Please don't do this. This is running with scissors. Then I am going to set statistics IO and time on so that I can measure queries and turn on my actual execution plan. I also put a note in here to open Task Manager. We're not going to be paying attention to this for the purposes of this demonstration, but know where my CPU is now. And when we get to compressed indexes, that's going to change. Okay, so an example for index views. Here's a reporting style query that my business has. We have sales by customer by product. So we're joining three tables together. We're selecting columns and doing some aggregations. Let's go ahead and run this query. You can see we get back about 79,000 rows. If I look at my statistics IO, I can see that on the sales order detail table I'm doing 2,400 reads. Sales order header has 58. Customer has 123. And my execution plan is a little bit messy, I would say. You can see I have clustered index scan, and a non-clustered index scan. Overall cost of 8.1 on this query. For the purposes of this discussion, this does not meet our business requirements. Right now it's managing to meet our time requirements at just under 80,000 rows, but we're only dealing with a very small subset of the data, and we know that this is going to scale up. What can we do to make this more efficient and faster? Let's turn this into an indexed view. Step one, turn it into a view. So as I said, there are definitely a few things that you have to be aware of going into this when you actually create the view. First off, ANSI nulls and quoted identifier must be true for the database. And sometimes this is the opposite with like third-party vendor software in particular. Just something to know if you're having problems creating it, that might be why. So you'll see I will create the view. I'm going to call it sales by cost by product. I'm going to have my with schema binding option put in. Because I have some aggregations and a group by in it, I have to include the count big function. This is for the internals of SQL Server, making sure that it knows how many records are in each of my groups. Again, I can't reference other views, I can't reference tables in other databases, and I have to use two-part naming conventions. I'm going to go ahead and create my view. Done. Now, what's the difference if I go ahead and I just select those same columns, my customer ID, product ID, order quantity, and line total from my view instead of using the tables? Looking at statistics IO, well, there's really no difference. We're still accessing sales order detail, sales order header, and customer. If I have an execution plan, it's the same. 2 clustered index scans and a non-clustered index scan. My query cost has not gone down at all. So this is one of the benefits of views. It makes queries easier to write, but it doesn't make them any more efficient natively. But now I'm going to go ahead and create a unique clustered index. I want to go ahead and do that on the customer ID and product ID columns. All right, SQL Server goes ahead and creates it, and now it's a persisted object on disk. Those index pages exist. I'm going to run exactly the same query I ran up here, selecting from the view. Looking at this, wow, that just got a whole lot better. Rather than having to read from 3 individual objects, performing almost 3,000 reads, we're now down to reading from one object, 454 logical reads. And if I look at my execution plan, it's gotten a whole lot simpler. We're simply doing a clustered index scan on sales by customer by product. So you can see this is a pretty hefty performance increase. Imagine if this was 79 million rows instead of 79,000. It can make a really big impact. Now, one thing to notice, my query plan does have an exclamation point over it. If I hover over that and it brings up the yellow box, down at the bottom it says warnings, columns with no statistics. One of the things to be aware of is that with SQL Server Enterprise Edition, which I am using for the purposes of this demonstration, SQL Server does not automatically create and consider the statistics on indexed views. I've written about that in some blog posts and articles. I won't go into that too much here today, but just be aware of that. So I mentioned Enterprise Edition because if you have Enterprise Edition, queries that can use an indexed view will automatically use it. But if you have Standard Edition or any other version, you have to include this with no expand hint. That tells SQL Server, when you run this query, do not expand the view. So I'm going to execute that. Notice that when I do, I get the same statistics IO results, logical reads 454. Notice here now that, and you guys can't see me, I had to turn my webcam off because of limited bandwidth, but I'm waving my hands madly about. I'm all excited, like, look, the yellow exclamation point went away. When you use the with no expand hint, you're telling the SQL Server, consider the statistics that are created on this object as well. So if you were using Standard Edition, you would have to use the with no expand hint. Even with Enterprise Edition, although you don't have to use that hint, I recommend it because you can get better statistics usage out of it. Now, what happens if I were to run that original query? Remember way back at the beginning when I wanted to select from 3 tables and do a couple sums on it? I'm going to run that query now again. When I do, I'm going to go back and look at the statistics IO and look, we're only accessing one object, sales by customer by product. We're doing our 454 reads here. And the execution plan has just a clustered index scan. This is called indexed view matching. With Enterprise Edition, SQL Server will, again, do this automatically. If you have a query that could use the indexed view, it considers it just like it would any non-clustered index on that table. So keep that in mind as well. Now, what happens if I want to add a where clause? I mean, we do that with our queries, right? We don't always just pull back all of the results from all of our tables. I hope, you guys. So what happens when I do that? Well, looking at the statistics IO, again, I am merely reading one object, sales by customer by product. My execution plan is a little bit more complicated. I have my stream aggregate in there, but essentially I'm only touching that one object, clustered index. Now I want to look at it a different way. This time, instead of querying it on the product ID, I'm going to query it on the customer ID. And, my statistics IO look a little bit different. This time I am accessing all 3 of the underlying tables. But know that the number of reads I'm doing are much fewer. If I look at my execution plan, I can see clustered index seek, and clustered index seek, which is different than the original scans that I had on my first couple queries. What's going on here? Well, the query optimizer is hard at work. It's doing what it always does. It's deciding the fastest, most efficient way to run the query. You can't always outguess the optimizer. And if you thought that the indexed view would be faster, you could shove in there and say, hey, make it use this by using an index hint. But then you're bossing the query optimizer around. It is smarter than you when it comes to running queries, despite how good we feel some days when we conquer certain queries. So remember, the indexed view is just a unique clustered index. It is just another index for SQL Server to consider when the query optimizer is when the query optimizer is making its decisions. So, again, I could use a no expand hint here, saying, I want to access the underlying, or I want to access the view directly. I don't want to access the underlying tables. Another benefit of having a unique clustered index on a view is that then you can create additional non-clustered indexes on that view, something you cannot do without the unique clustered index. So here I'm going to create a non-clustered index. I'm going to make it on my customer ID column and include order quantity. There we go. It's created just like any other index would be. Now I'm going to create a very contrived query to select the customer ID and the sum of their order quantity. Let's look at that execution plan, and we'll see that we are very specifically using that non-clustered index, sales by product, customer ID, order quantity. Non-clustered indexes, just like a non-clustered index on a table, will help us satisfy individual queries. But again, we don't want to be putting too many non-clustered indexes on either tables or views. Every non-clustered index we have is one more write we have to do every time we do an insert, update, or delete. So let's just check a couple other things. What happens if I alter one of the base tables? I try to change the sales order detail column order quantity and change it from a big int to an int. I get some errors. There are a lot of dependencies on that. Among other things, the sales order detail and line total table. So this is part of that with schema binding option. And just trying to show you a couple of things here, trying to insert into the base tables. Is there anything special about that? Just doing an insert into the sales order header? Nope, that succeeds. Remember, this is just another index that exists. So it's doing another write, but it can go off flawlessly. As I mentioned, there's a couple of SQL Server and database level options that need to be turned on for an indexed view to succeed. The biggest one I usually see is ANSI nulls on or off. If I set ANSI nulls off and then I try to do an insert into one of the tables, we'll get an error message that the insert failed because the following set options have correct settings, ANSI nulls. So be aware of that. Okay, and that, I'm going to turn that back on so there's no more failures. So that's the indexed view. Again, to persist the pages of the view on disk, create a unique clustered index on the view. Let me see, we did have a couple of questions. Mostly, what is the impact of the indexed view on the base table? Again, for every time you read, or I'm sorry, every time you do an insert into the base table, it will see if the columns that are in the index view need to be updated, and if so, that's an additional write. Same thing with updates and deletes. Again, the more frequently you update base tables, the more frequently this, like any other index, is going to be updated, so just be cautious. All right, so let's go back to our Safari and talk about the next wild and mythical Okapi, the filtered index. So when we write our queries, I even showed you in the index view example, we don't just write a select and a from, because otherwise we would get every row from every table every time. That's fine if our tables contain 10 rows. Whose database has every table containing 10 rows? I'll bet all of you are laughing at me right now. We create a where clause on our queries to filter down our result sets. We want to look at specific customers. We want to look at specific order dates. We want to look at the details on storms that only occurred in Nebraska in the month of August. We want to view data about the moon in 1963. If you have a job where you get to view data about the moon in 1963, awesome. But again, this doesn't help with the amount of data that we have to read off of the index. So it's like a sales order table. If that sales order table has 1 million records, even if you're only going to pull back 1,000 of those from December of 2013, when you go to do an index seek or even an index scan, SQL Server still needs to read all of the pages in the index. However, you can add a where clause onto a non-clustered index. When you do that, only the records that meet that where criteria are stored in the index pages. So the indexes are much smaller to begin with, meaning that when you actively query those indexes, you do fewer reads and they're faster. They also include filtered statistics. So remember, with the index view, sometimes it doesn't recognize the statistics. With filtered indexes, it does. The reasons to use filtered indexes. Number one of the reasons I see it most commonly used, you have a column of data where 90% of the time the value is null, 10% of the time there's a value, and the only time you ever query it, you just want to get that 10%. So you could create a filtered index where column is not null. Only non-null columns will be stored. Very efficient. The other thing that I like to think of it as is kind of a status column, where you have a bunch of you just have a bunch of values in a column, but only one or two of them are queried very frequently. I'm going to use my sales order example again. Your orders have statuses. The order's been placed. The order is open. The order is in packing. The order is being shipped, then it's invoicing, then it's closed. When your database is new, when this application is new, you probably have a fairly even distribution of values across most of those statuses. But as time goes on, you get more and more and more in the closed status, right? So you go from having 25% closed and 75% in these other statuses to 75% are closed, 10% are open, and the rest are distributed. What if you have a report where you just want to view the orders that are in the problem status? Wouldn't it be great if you could just create an index that holds only those objects? You can. It's called a filtered index. Again, you're creating another index on a table. So if you're going to be creating this on columns that are updated frequently, understand that you're going to have read and write impact. Can you use filtered indexes anywhere for everything? No, unfortunately you can't. So first off, understand that this was first available in SQL Server 2008. So if you're still on SQL Server 2005, you won't be able to use that. And please consider upgrading soon. Support for 2005 ends in a couple years. You can only create an index on a single table, just like any other index in SQL Server. It has to be simple comparison operators: equal, greater than, less than. Something like between is not allowed. The index must satisfy the entire query. It must be a covering index. This is one of the biggest reasons I see that filtered indexes fail. People say, I created this, but it's not working. What did I do wrong? I'm going to show you an example of that so you understand exactly what it is. And also, they won't work with local variables or parameterized SQL unless you perform some special tweaks And although although filtered statistics are included, the auto update statistics doesn't affect this. That only affects the base table. So if you're really getting hard and heavy into filtered indexes, you have this one that's really important to you, you might need to set up a SQL Server agent job to update the statistics on that particular index on a regular basis. Okay, let's see this in action. I'm going to go ahead and pull up SQL Server Management Studio and give you a demo of this. Again, using SQL Server 2012, this would work with 2008 R2 as well. First, I'm going to show you that null example. Here I am going to be querying my product catalog. I want to look at product information. Note that color, size, weight, these have a lot of null values in them. When I look at my statistics IO, I'm only using one object, the big product table. I'm doing about 600 logical reads. So now say that I want to rewrite my SQL statement so that I am only looking for products where the size is not null, so they have a size defined. In this case, my number of rows returned is much smaller, only 10,000. But if I look at statistics IO, I can see still 600 logical reads. So I'm returning less data, but I'm doing the same amount of work. That seems silly. Let's try to create a filtered non-clustered index. So here's the syntax for it. Create non-clustered index, give it a name, tell it what table it's on, what the key columns are, and then where size is not null. Done. I have another index. I can even verify that by going to my Object Explorer on the left, expanding big product, and expanding indexes, and I can see product, size not null. So now I'm going to rerun this query. All of it, not including the S in select. So I get the same number of rows, 10,549. Wait, Jess. We're still seeing 600 logical reads. Let's look at that execution plan. Yeah, I am still doing a clustered index scan on big product. So I created this filtered index. It didn't work. What's up? Remember how I said that it needs to cover the entire query? So the filtered index has to include all of the rows from the table that you are referencing. So if I wanted to make this an effective index, I'm going to drop it first off. And then I am going to recreate it. And this time I'm going to recreate it by having the same key column size. I'm also going to include the other columns I'm returning in my select statement. And then I'll have the where size is not null. Okay, it's created again. Let's rerun that query one more time. All right, 10,549 rows. And boom, we have reduced our statistics IO significantly. We have gone down to 139 logical reads. That's less than a third of what we initially had. So this is the benefit of filtered indexes. They can be a little bit difficult to set up. And they can be kind of picky about what queries use them and what don't. But when they do work, they're really powerful. Let's go ahead and look at another example of it. Why did people order from us? So I have this sales reason table in my database. When we add orders, we're talking about, did they order from us because of the price, because of the manufacturer, because of something we sponsored? So when I query for my orders, I want to join sales order header, sales reason, and then that sales reason table. So these are all of my orders and why that order was placed. You'll see, as expected, my statistics IO shows me scanning all three of those tables. So I'm doing 88 reads on sales order header sales reason, 689 and 2. Execution plan, I've got a clustered index scan, clustered index scan, clustered index scan. But I don't always want to pull back every reason for every order. In this case, I just want to look at which customers ordered from us when they saw that we ordered, or after they saw a television advertisement. Sales order header reason ID 4. When I run that query, you'll notice instead of getting 10,000 some rows, I get 722. But if I go to messages, sales order header sales reason still shows 88 logical reads. No more efficient. You can see we've still got the clustered index scans and seeks. Let's create a filtered non-clustered index again. So here, I'm going to be creating it on the sales order header sales reason table. My key column is sales reason ID, and my sales reason ID is 4. Now you'll notice that I have a clustered, I'm sorry, I was looking at the execution plan to create index statement. That's not what we want to look at. We want to rerun our query where we are selecting only sales order header sales reason ID number 4. You'll notice I still get my 700 results. Notice the big difference here with that filtered index applied. Rather than having to do 88 logical reads, rather than checking all of the reasons people are ordering from us, I am merely doing 4 logical reads. That's a vast improvement. Looking at the sales order header sales reason, now it is a non-clustered index seek rather than a clustered index scan. Much more efficient, reduces our I/O dramatically. If I want to, I can even use my DMV, the sysdm db index physical stats to look at the indexes that are available on this table to see the difference in size. So here's our primary key, or clustered index. You can see that's 86 pages, and that non-clustered index, that filtered non-clustered index, is only 2. Significant difference in size of the index and the I/O required when we're reading from that index. I see there are some questions in the queue. Be getting to those when I'm done with this section or at the end of the presentation when I have a minute. Let's just look at a few things that people have asked. Can I do this in the where clause? Can I do that in the where clause? So what if I want to look at everything but sales reason ID 1? So I want to see everything but price. Could I do where sales reason ID not in 1? Run that, I execute it, and I get an error message. Incorrect syntax. So no, remember, it's a simple comparison operator only. So can I do in? Can I specify that I want sales reason IDs 2, 3, and 4 instead of just not in? That I can do. So you could use the in operator. A lot of questions in filtered indexes revolve around dates. Can I use a date column? Sure. Let's look at the sales order header table and the order date column. I want to create a filtered index only looking at order dates greater than January 1st of 2013. It succeeds. Again, we have a simple comparison operator, just a greater than. Sometimes people have asked me, well, can I do a date range? Could I store all of my orders for 2013 in a filtered index? Let's look at this where clause. The order date is greater than or equal to January 1st of 2013, and it's less than or equal to December 31st. Yes, absolutely, that succeeds. We have multiple predicates, but they're on the same column, and they're simple comparison operators. What you cannot do is use something that is, again, non-deterministic. So these succeed because you're always going to have a static order date. And an order date is, it's either going to be greater than or equal to January 1st, 2013, or it isn't. But when we try to do something like use a date add function, I want to say filter my index only showing order dates that are within the last year. That's when I get an error message. Incorrect where clause for filtered index. It's not deterministic, so it can't be used. Also, one other quick limitation, as I mentioned, is local variables. So say rather than declaring, or rather than putting that sales reason ID equal to 4 directly into the where clause, I do a variable. Sales reason ID int equal to 4, and then I write my query where the sales reason ID is equal to that variable. Let's execute that. We still get the same amount of results at 722 rows, but let's look at that statistics IO. Note that on sales order header sales reason, I have 88 logical reads. That's my initial value. And if I go to the execution plan, I see a clustered index scan on sales order header sales reason. The reason for this, in order to use a filtered index, the query optimizer has to know what value you're passing into the index. When you're using a variable like this, SQL Server can't determine that until runtime. Thus, it can't use a local variable in this particular instance. Okay, so a few questions here. Can the filter use a subquery? No, you cannot use a subquery in the where clause. Can you use something like a year function on the date column? No, so you can't use date, you can't use month, you can't use year. All of those are different functions. A couple of questions about will the demo code be available? Yes, I will make sure that I get Gabe both the slides and the demos for this, because the best way to learn about this stuff is to play with it. Are filtered indexes persisted like indexed views? Yes, this is simply a non-clustered index. The only difference between a filtered index and a regular non-clustered index is that it contains fewer rows. That's it. And Bill had a question about what was the command that turned on the details about the number of reads. That is set statistics IO on. That'll be in my demo script. So that's the filtered index. Again, a little bit pickier about when and where you can use it, but when it's usable, wow, does it make a difference. With time winding down here, I love talking about SQL Server so much, it's hard for me to talk about it in less than an hour. I'm going to go ahead and talk about our last option here, compressed indexes. SQL Server data compression is a beautiful thing. When I was at DBA, I liked it because it helped me from a management perspective. It took, these tables that were dozens or hundreds of gigabytes in size suddenly could be reduced to under 100 gig. It physically takes up less space. The beautiful thing is that data compression can be applied not only to clustered indexes, but it can also be applied to non-clustered indexes and even the indexed view, unique clustered index. Without going too much into the details of compression, that's a different subject entirely. We'll talk about, you can have two levels, row or page compression. With some data types, row compression is best. With other data types, page compression is best. What happens is instead of a page being able to fit 100 rows on it, when it's compressed, you can now fit 800 rows on it or 1,000 rows on it. I've seen compression reduce tables down to 30% of their original size, 40% of their original size. when you're storing more records on an individual data page, that means you do fewer reads to return the same number of rows. So this is another example where you can reduce the I/O that you are using to pull back the results of your queries. So really, the best reasons to use compressed indexes would be reducing the space used to store your data. This is helpful from both a management perspective and from an I/O perspective. Also consider that when you reduce the space on disk through compression, data compression carries through to memory. So when you reduce the number of pages that you are taking up on disk, you also reduce the number of pages that are read into memory. They stay compressed there, so it can help you use the memory on your SQL Server instance more effectively. There are a couple of big drawbacks to compression, however. Number one, it's expensive edition only. Yeah, you have to have SQL Server Enterprise Edition to be able to use native data compression. It will increase your CPU usage. When I run my demo, you're going to see that the biggest CPU hit happens when you initially compress the index. But overall, as you continue to have compressed indexes on your system, new data pages have to be compressed as they're being written to. You're going to have an overall maybe 10%-ish increase. So if you have a database server that's hovering, 30-40% CPU usage normally, sure, no big deal. If you have a CPU that's normally pegging out at 80-90%, I would reconsider doing compression here. The other thing is that some data just doesn't compress well. If you have a varchar 100 column and on average you're using up 90 out of those 100 characters, you're not going to get a ton of compression. There's just not a lot to get rid of there. If you don't have a lot of repeating data, you're not going to do very well. And lob data, anything that's off page, won't be compressed down either. So let's look at a couple of examples here just to see how beneficial this can be in some cases. Oh, went one too quick. Previous and Alt-Tab. All right. Back in SQL Server 2012, I'm going to be using the big transaction history table that I have here. Let me slide that out. I'm going to first off use some system views to look at the size of the indexes here. So my big transaction history table has a clustered index primary key. Notice that it has 143,000 pages, taking up about 1,100 meg, roughly a gig in size. It also has a non-clustered index on transaction date, about 131,000 pages, taking up just over a gig. I can also see this information if I come to Object Explorer, right-click, and select Properties, and then go to the Storage table. I can see that I have 1.1 gig of data and just over a gig of indexes. Now say that I want to run a query against this table. I want to select transaction dates equal to February 16th of 2007. I'm going to tell you this is going to run for a few seconds. This table not super efficient. If I look at my messages, I can see that I did, 132,000 logical reads. And that even managed to go parallel, non-clustered index scan there. Okay, so that's a pretty big hefty query. Perhaps I want to try to apply compression to make this more efficient. How would I go about doing that? What I do is I issue an alter table command. So I alter the table and I rebuild it with data compression equal to row. I'm going to start with row rather than going directly to page. And now we wait. and we watch our CPU usage spike. And we wait for a little bit longer. Don't worry, you're going to keep waiting. And this isn't even a truly terribly large table. This is what I meant when I said that when you go to initially compress a table, your CPU usage is going to spike and you're going to be waiting a minute. It's a pretty intensive operation for SQL Server to condense all that information and rewrite it. The other thing to note is my statement says specifically alter table, rebuild. Rebuilding a table is an offline operation. You cannot make compressing or uncompressing a table or index an online operation. This has to be done during off time. So it's done. Now, let's see, did that help? Let's rerun our query for orders that have a transaction date of February 16th of 2007. It seemed to go faster, right? Was that just my imagination? Remember, we had about 132,000 logical reads previously. Statistics.io proves it was not my imagination. I have reduced that down to 91,000 logical reads. My execution plan still shows a parallel clustered index scan, but I read fewer pages. Let's take a look at the table properties, go back to storage, and see our data space has gone from 1.1 gig down to 700 megabytes. So we've reduced it about 30 to 40% here. I don't know the exact number, but that's pretty significant. Notice, however, index space has not changed. All I did was choose to rebuild the table. I rebuilt the clustered index. So understand that when you rebuild a table, when you do the clustered index, you're not affecting the non-clustered indexes. Those have to be done separately. And in some cases, you may want to leave the table, the clustered index, uncompressed and just compress one or more non-clustered indexes, or vice versa. And that's perfectly okay. You can compress just one index if it's the most important index. Nobody says you can't. To compress a non-clustered index, instead of issuing an alter table rebuild, we issue an alter index rebuild command. And again, we watch CPU usage spike, and we wait for a minute. And we wait. Yep, we're still waiting. And this is on a local instance. I have 16 gig of RAM on this laptop, and we are still waiting. All right, good question here coming in. What happens if you run your application on Enterprise Edition, but then what if you need to move it over to something like SQL Standard or SQL Server Express? Would you have to rewrite all the table generation and index creation statements? Yes, you would. You cannot use compression on SQL Server Standard Edition or SQL Server Express Edition. Another thing to note is that if you have compressed tables in your database and you take a backup of that and you try to restore it onto Standard Edition, it will fail. You would have to uncompress, back up, and then restore. So keep that in mind as well. All right, now I'm going to rerun my size here and just double check that both my primary key has been reduced down to about 709 megabytes, and that other index, which was just over a gig, has been reduced to 710 megabytes as well. So we're definitely reducing the number of pages that store the index, which means fewer reads to return the same amount of data. Now, as I mentioned, row compression is kind of level 1. The step up is page compression. So page compression is row compression plus additional work. I could issue an alter table rebuild with data compression equal to page, but we've already seen how much work it takes to compress a table. So I've already kind of pre-done this one. I'm going to go to my table big transaction history page, go to properties, and just show you the difference here. If we look at this, we have the same number of rows, and now our data is down to 625 meg in size. So remember, we initially started with an uncompressed clustered index at 1.1 gigs. We moved down to 700 and some, and now we're down to 600 and some. Different data types will compress to different levels. You're going to have to play a little bit with it in your system to determine, is this table going to benefit more from row compression or from page compression? Now, one neat thing to know, and I'm going to cut this demo a little bit short because we're close to an hour, but if you have a question about how much would compression help, SQL Server is here to help you out. Now, you most certainly could take your database, back it up, restore it to a development instance, hit alter table, rebuild with row compression or with compression equal to page, and just wait and figure out how long it's going to take and how much savings you'll get. Or you can use the stored procedure SP, estimate data compression savings. You pass in the schema, the table name, the index ID, the partition ID, and compression type, and it gives you an idea of how much space you could save. So say I want to run that on my production schema and product table. I'm checking the clustered index or index ID of 1. There's only one partition, so partition 1, and I want to see what row would provide. Okay, so size with current compression, which is none, is 120K. Size with row compression estimated to be 72K. That's almost 50%. That's not bad at all. I'd consider using it. One thing that this does bring up then is, wait, Jess, I can pass in a partition ID. Could I compress just one partition of my table? Yeah, you certainly could. It's very flexible that way. So that's the benefit of data compression. While you do have to be running SQL Server Enterprise Edition to take full advantage of it, when you can apply row or page compression to a clustered index or non-clustered indexes, you're going to be storing the index on fewer pages, so you're taking up less space on disk and you're taking up less space in memory, and you're also making it do less work because there are fewer reads that need to be done. Don asks how compression affects updating the table. As you do inserts, updates, and deletes, you're going to be creating new pages. The compression affects when new pages are created. They have to be compressed down. So when a page fills up, it gets compressed. This adds to the CPU overhead on your server just a little bit. Again, it's not a 40% increase. People that are using compression typically see about a 10% increase in CPU usage, but you don't need to change your insert, update, or delete statements. It's nothing that you need to modify there. There's no special, you don't need to add with row compression or with page compression to your insert statements. SQL Server does all of that on the back end. All right, so I have talked through indexed views, filtered indexes, and compressed indexes, the Okapis of the SQL Server database world. Again, there are some narrow use cases for some of them, but when you do find those use cases, they can be incredibly helpful. So in this slide deck, which will be available to you, I have some additional resources on indexed views, filtered indexes, and compressed indexes. With that, if you have any questions, please feel free to contact me. My email address, jess@brentozar.com, and again on Twitter as girl, GRRL_GEEK. Gabe.
Yes, that was a great presentation, and we did have, we had some amazing questions and participation
thanks for
going
the
on.
questions, you guys. Love questions. And if there are any I didn't get to, Gabe, if you can send me the questions, I'll just go through and make sure I follow up individually.
Sure, not a problem. And
Cool.
this session will also, it has been recorded and also be available in our YouTube channel. And you can link through that at appdev.sequelpass.org when it's available. And you can I guess, check the presentation out again. And I guess that would be all for a Friday, noon,
Cool.
or whatever time you are in your part of the world. Thanks again to everybody, and thank you, Jess, for speaking to us.
Yeah, thanks for having me, and hopefully I'll be able to bring another topic to you guys sometime in the future. Have a great weekend, everybody.
Yes, thank you very much, everybody. Goodbye.